Hi guys, today I'm going to show you the mechanism of Pinacol Pinacolone reactions. This is very common lab experiment in most organic 2 labs where you take some benzopinacol and you heat it to reflux with some iodine as a catalyst and some acetic acid, and you get the product, which is benzopinacolone. Notice that this is a 1,2-diol. Let me write that down for you. So benzopinacol is technically a 1,2-diol that's getting reacted, and the product gives you a pinacolone, which is a ketone. Notice the O-N-E suffix, so you know that your product is a ketone. You can also identify that you have 2 OH groups, and one of the OH group is lost in the final product, while the other OH group is turning into a ketone, and we still have all of our 4 benzene rings. Okay, so let's get started with the mechanism. Okay, so our first step is to protonate one of the hydroxyl groups. You can use either or because they're both equivalent. I'm going to protonate it using the H from my acetic acid. You could have also used your catalyst as your source for protonation, but I think this way is easier for you to see what's going on. So now I have a carbon with the oxygen that's bonded to 2 hydrogen, and it gives you a positive charge on the oxygen because now it has an extra bond. Notice that we have a good leaving group, which is the water molecule. And so our step 2 is to lose the water molecule to give a carbocation, a tertiary carbocation, that is. So I'm going to go ahead and draw that. We're going to lose the water molecule. So water molecule says bye-bye. Okay, water molecule leaves, and we get this structure right here. Okay, we get a phenyl bonded to a carbon. And now this carbon has a positive charge, and the oxygen here is still intact. Okay? Okay, now what you want to keep in mind is that even though this is a tertiary carbocation, it could form even a better carbocation, which is a resonance stabilized tertiary carbocation. So our stability for carbocations are tertiary with resonance beats tertiary by itself, which beats secondary, and you'll never usually see a primary or a methyl carbocation. Okay, those are relatively unstable, so you don't have to worry about that. Okay, so with that said, how can we change this tertiary carbocation, which is already really stable, how can we change that into something even more stable? Notice that if we migrate one of the phenyl ions onto the carbon to make it happy, we get this structure right here. We get a phenyl bonded to a carbon, bonded to, I'm sorry, this one, yeah, I don't know what I'm doing. I messed up. Okay, so this carbon is now bonded to a carbon, which is bonded to 3 phenyls, okay, because we just shifted one of the phenyl onto the carbon. And now this carbon is bonded to the OH, and it carries a positive charge because we just lost the bond that used to be here, okay? So now this carbon is missing a bond, and now it has a positive charge. Now, what you have to realize is that there's a huge difference between this tertiary carbocation and this one. This tertiary carbocation is in resonance with the oxygen, okay? So the oxygen's non-bonding pairs can be in resonance. So the lone pairs can come in to satisfy the octet rule for the carbon. So to draw my resonance, I draw my brackets, my double-headed arrow, and let's go ahead and draw the structure. I still have the phenyl here. Carbon is now double bonded to the oxygen, which is still bonded to the hydrogen, bonded to a carbon, which is still bonded to the 3 phenyls. And notice that now we have the positive charge on the oxygen because now oxygen has this extra this extra bond with carbon, and oxygen usually wants to form only 2 bonds. Now that it forms 3 bonds, we have a positive charge. Okay, let's close our bracket to show that this is our resonance structure. Now let's determine which is the major and which is the minor product. Notice that this structure fills the octet rule for all of our atoms, but this structure does not have an octet rule for the carbon since it has a positive charge and it lacks the octet rule. In here, in this structure, oxygen, carbon, phenols, everybody is happy because we have the octet rule. So this is my major structure, okay? And this is the driving force of the Pinacolone reaction. The extra stability from oxygen's lone pair helps to stabilize the positive charge on the carbon through resonance, okay? So our last step is to deprotonate this H to give you your final ketone product. To deprotonate, I'm going to go ahead and use my conjugate base from my acetic acid. Here's my conjugate base, okay, with the negative charge. Is going to come in and pull off the H. The bond is going to go back to the oxygen. This gives me my final product, which is a ketone. Phenyl, carbon double bonded to an oxygen, bonded to a carbon, bonded to D3-phenyl. Here is our final product, benzopinacolone. So what you really want to get out of this whole thing is that the pinacolone reaction occurs because of a carbocation rearrangement that goes from a tertiary carbocation, which is already stable, to a even more stable tertiary carbocation through resonance, which drives this dehydration of pinacol, which is the 1,2-diol, to the pinacolone, the stable ketone product. Hope this helped. If you have any question, give me an email, and I'll leave a link to my email at the bottom of the description box. Thank you.